Our FCT circuit, lab number 35. We'll record this because Wesley's not here tonight. He said they're putting them on like 60 hours a week or something like that. They got some big order. Okay, guys. Where do we start? Y'all got the lab book? I don't. What's our first base voltage we're going to do? So this guy is VG, right? This guy is VDD. This guy would probably be VGG, actually. Okay, guys, what do I need to do first? What are we going to measure? Tell me what we're going to measure. What measurements we're going to have to make? Okay, so drain to source. So we'll put a voltmeter right here. What other measurements do we need to make? Make sure it's set up here. Let's see. We'll make it, we'll give it a real high input impedance. But it should be set for DC volts. Okay. What are the volts we need to measure? Yeah. That other one is on. Okay. Which one's R2? So here's R2. Don't want to do that. So we'll put a voltmeter across this. So what else we need? That's the only two voltages we're going to measure. We're not going to measure gate voltage. Are we going to measure it here, or are we just going to change it right here? Huh? We're going to have to measure it, or we? Huh? And that's gate to source, right? Let's actually gate to source because the source is connected to common, right? Okay, so what are we going to do? We're going to start off with this guy probably equal to what? Okay, we'll start it equal to 0. So our, let's go, I'm going to extend this down right here. And then let's put an ammeter in here so we can watch the actual, so as we turn this guy here, as we bring the gate to source voltage on, we should expect this, the current to go down, right? So this will be maximum current right here. Now, of course, they want you to calculate it. So that's probably why we want to measure the voltage drop across here, but we'll go ahead and measure it too. Okay, we're ready? What do we want our drain voltage to be? This guy's going to 1 volt to start off with. And then we're going to, this is the guy we're going to vary, right? Okay, so we're ready? No? Yeah, 1 volt. All right. That's it, VDDs. Okay, so we're ready? All right, everything ready? Ready to turn it on? Okay, so we got a voltage drop across R2 of 23.94 millivolts, which when you calculate this out, this is going to be 239.3 microamps, right? Y'all not asking that? Well, I can't make it any bigger. Well, I can make it a little bigger. But I can't keep it bigger and get, we got plenty of seats up here. This is as big as I can get it, guys, and still keep it on the display. That's like sitting in the very back and complaining because you can't hear the preacher. And they got all these seats up front. So yeah, we got plenty of room up here, guys. So if y'all can't see it, then y'all need to move up. It's just they're going to ask you to calculate current. All you do is just move it over, right? Okay, is this everything? We got everything you'll need? Huh? Oh, okay. So I don't know what they mean slowly. So how slow do we want to go? So here's 0.2 volts. Okay. Here's 0.4 volts. You're not supposed to be making this measurement. We're just looking, right? Okay. See what's happening now is as we increase VDD, then the current's increasing. Now we're going to get to what we call a pinch-off voltage. Here's 0.6. So it's still going up. Here's 0.8. Okay. But if we looked at the ratio is slowing down right here. So what we're doing is we're seeing it start knee. And then here's 1. Now 239.3 microamps, or actually 239.4 according to this measurement right here. Okay, so y'all filling in the chart? What y'all need? Are we okay? No? Okay. So let's go to 1.5. That's too much, right? 1.2. I don't think we're going to do much better than that. There's 1.75 volts. Oh, to get a reading across it of what? 1 volt? Okay. So that's 976 millivolts. That's the best we can do. So 1.1 volt gives us this close. I could probably play around with it a little bit, but so now we have 244 millivolts, which would be, 24.44 millivolts, which would be 244.4 microamps, right? Looks like this meter's off just a hair. 1/10 of a microamp, though. Okay, so what do we do now? Take it to 2 volts. Huh? So we're going to leave this at 1.1. Yeah. And then we're going to put 1 volt on the gate. We okay? You can see that? Huh? That's -1. I probably have to raise this a little bit. That's about the best I can do. We okay? We okay? We okay? So what we're going to do next? 2 volts on the gate. That close enough? I shot it. I did pretty good on that one. So we just about got this guy cut off, don't we? I'm not sure why this and this don't calculate out the same. Okay, what's next? Okay, so we're taking the gate back down to 0. We're going to raise this till we get 2 volts across there, right? Can't do much better than that, can we? So we got 0 volts on the gate. We got 25.02 millivolts across R that. We have 2 volts across DS. So this guy's measuring DS, right? What we're going to do now? Notice as the gate current gets more negative, the drain current goes down, right? And guys, use your resistor up here. Don't use this ammeter. I need to take that out. It's don't look like it's doing it quite right. Okay, what do we need to do next? To -2. Oops. Okay, that's -2. Just about cut off, ain't it? Yeah. Okay, what do you do next? Huh? Yeah, because we're at what they call the pinch off voltage, which means this is so this is going to work kind of like the and I can't draw this. This is going to work kind of like the transistor, but the transistor came up and did like this, right? This guy right here is going to come up with a slant and then it's going to level out. Okay, so we need to break this up to 1 volt now. And what's our VDD supposed to be? Oh, we're at 3 volts, so that's still okay. But notice as the gate source voltage gets more negative, the transistor starts moving toward cutoff, right? Are we okay? We got it? Now we need to move to -2. Looks like for this guy, about 2 volts is the cutoff voltage on it. Okay, what next? A VS 4.5? I mean 4. We'll drop this back down to 0, right? So look, we got the same current here. So even though the drain to source voltage is changing, we get the same current right there. 250, isn't that what it was before? 250 microamp? Yeah. So we're up past the knee. Okay, we ready? Then we want to go to what? Now 1. We okay? We ready? We'll go to -2, right? And the guy should just about cut off. Yeah, same thing right down here. I don't know what this math down here. The math is wrong. Looks like the simulation's having a little problems. Okay, guys, any more? We're gonna jump up to 6. And drop this guy back down to 0 again. 250 micrograms. So notice, even though the VS is changing, well, when the guy is turned on, it's the same current, because that's the way the bipolar transistor is. So what it does, it allows this output right here to change and not change the actual current flow through the. Okay, so we'll go up to 1 again here. Should start turning off now, right? About the same, right? Huh? They use R2 here. That's what we're doing. This guy when we just about cut it off, this guy starts having problems. And you see it's still having a little problem in this math right here. I need to take this meter out. So use this voltage right here to calculate your drain current. Okay, we ready? So it looks like the cutoff on this guy is pretty close to 2 volts, minus 2 volts. Any more? Huh? 8? Okay. 250 microamps. Actually 251. Okay? There you go. All right? Ready for the next one? So any more? Huh? 8 was the highest one. And this is what you need. Look how much current, according to this thing, how much current we're putting into this. I'm not really sure. I don't think these should match, but you have to understand this guy right here is providing basically no current at all. To get what? To get this current over here. So these guys have extremely high input impedance. So this guy here would be ideal using something, a source that's got a high input source, right? You understand that? And like I say, you'll run into these on radios, you'll run into them on a lot of things where we input. Now this oscilloscope, if I looked at the input on this oscilloscope, I guarantee it comes into an FET. So the first thing it sees when the scope probe comes in there, I guarantee it's probably going to be an FET. Because we don't want our oscilloscope to put a big load on our circuit, right? Y'all understand that? Pretty neat. Y'all got any questions on this? Anything we need to go back over? So you get the maximum current when the gate source is equal to what? 0. And that's why these things here operate in what we call the depletion mode, which means as we increase the gate to source voltage, the FET actually does what? Starts cutting off. And we call that depletion mode operation. So that's FET. It's a JFET though. This is the junction. So there is an actual junction that we never want to forward bias between the gate, the gate and the source. So we operate these guys in depletion mode. So when we bias them, somehow we're going to bring this guy here negative, a little bit negative, so the output, we're going to operate at class A. And that was what the other circuit was. It was actually biased, which is pretty neat. So you got any questions, guys?